Afternoon. This is Lee McWhorter, cybersecurity instructor for WazU. Welcome to the first section of the crypto and access management class that began today, actually. I usually do workshops on Tuesdays or Wednesdays, but I have a family matter I have to take care of midweek. Shouldn't take me out too long, but I just kind of complicates my midweek schedule. So we're going ahead knocking this first session out today. This class is a one class, but it is broken into two major parts. We spend the first four lessons really covering cryptography, and then we revisit it later as well as part of the last lesson. And then kind of in the middle is the access management part from like 5 through 9, or 5, 6, 7, 8, 9. And so, of course, we're going to follow the standard model. And this one, we're going to cover the first three lessons, which will all be cryptography stuff, cryptology stuff. We will cover those today. And then we will next week cover the middle four, like we always do, saving those last three for the final. I really love the first part of this course. It's one of my personal favorites because we talk about, what is cryptology? What is cryptographic kind of stuff? And basically, it is some mechanism by which we can take plain text, readable, human readable, regular text, characters, whatever the language theoretically, and we turn them into what we call ciphertext. We turn them into some kind of, ostensibly, at least to the average casual observer, to be meaningless, useless. That you can't read this anymore because it's been encrypted. And so there are all kinds of processes by which this happens in the world, particularly in our modern world. But what we start off doing in these first few lessons actually is providing a really cool history tour of sort of cryptography and sort of how it developed. Now, before we get specifically into some of that, which is mainly lesson 2, but let's talk a little bit more about why do we use cryptography? How can it help us? Well, of course, if we go back to our very first class, right, way back for many of you folks in this class, obviously, we had security foundations, and we talked about what I like to call the three promises we make in cybersecurity. We promise to keep data confidential. We promise to maintain the integrity of data, and then we promise to make sure that the data is available to our organization so it can accomplish its objectives. The good old CIA triad, right? Confidentiality, integrity, and availability. Well, one of the reasons that cryptography is so important to cybersecurity is that it can help us with arguably all, but the main two really. If in some way you can sort of protect your backup maybe, and that helps ultimately meet the availability need, then you could say kind of indirectly cryptography can help with that piece. But the two pieces of the two promises of the three that really cryptography goes a long way to helping us with are, of course, confidentiality. Because if we can take that regular human readable text and somehow massage and manipulate it into this unreadable ciphertext that we can then transmit, say, over the insecure internet, for example, and then be able to have that message maintain its confidentiality because of that process, then our recipient is the only person ideally who can read that message, and we've maintained that confidentiality. Now, another thing that at least modern cryptography ciphers can do is they can help us in the context of integrity as well. One of the things, and there are various variants of how this can be done, but many of you have, no doubt, even as part of this program, gone to various sites, maybe say a good example might be the Ubuntu site, to go and download an ISO file, the image, the disk image, the installer image that you could use to create, say, a standalone virtual machine. And I know that folks in this class have done that at least a couple times. We had it in network defense and in system admin, playing with different virtual machines, working with their networking, etc., and using some of their services like OpenSSH. So you get that concept. And most of you, all of you have done that, but some of you, if not all of you, probably along the way, and other sites are like this. A lot of the open source tools that we use and sites that we use, when you go to download that ISO file, if it's a CD image or a DVD image, or if it's just an installer, many times they will have what they call a checksum, or basically a hash value that they keep on the site. And the idea is that you can download that file from them, and then you can generate that hash value. And when you do that, if the numbers match, then you know no one has modified that file in transit, and that no one has changed it and inserted a virus or something nasty in there. And so you can feel, reasonably safe that, unless somebody had totally taken over that site and thus faked the key values or the hash values, the checksum values, then then we have a bigger problem, and so does that entity. But in most normal workaday situations, when you go to an open source site, or you get, even some companies do this, they basically have sort of run this hash value, run this checksum, and it's an algorithm that runs across the file and analyzes it and generates a unique number, ostensibly, to identify that file based on whatever the algorithm may be. And we'll talk more about algorithms and how they fit into the ciphers as we get deeper into this. You'll even do some hands-on in coming lessons to calculate sort of a proof of concept for the basics of public-private key, which we played with but haven't explained in as great a detail as we will in this course. So, but because of those kind of methodologies, and including in public-private key, if I send an email to somebody with an encryption and I encrypt it, and we're using that whole public-private key methodology like we did with, say, SSH, then it actually, that's one of the reasons we can use. If you remember back in Network Foundations, you had to create an Ubuntu VM, and then you had to set it up so that you could connect to it, from your own computer, but in a sense remotely connect in to that SSH server and log in and get a terminal. When you first did it, you used a username and password kind of model, and then you generated public-private key pair. And by doing that, that was how we ultimately turned off passwords so that we could log in through that public-private key pair, because that guarantees, if I've loaded the public key up on the server and I maintain securely on my machine the private key, when I connect with SSH using those keys, the system, without having my private key, when I send it, the information, then the public key and the private key match, and only somebody who has that private key would be able to have that mathematics work out, so that we can assure the authentication, who I am, my authorization, and who my identity is, and that will allow me then to log into that machine. If I'm just sending you an email message, and I use that same methodology, so I encrypt that mail, and I use your public key and my private key, which is the way it works, and then when you receive it, you flip that. Your software will use your private key and my public key to do the decrypting. That means that there's two things going on there. One, we've kept it confidential by sending that encrypted message, but we've also maintained the integrity because we can assure that, and there's another related phrase that you'll hear in this class called non-repudiation. And that means I can't send you that encrypted message using that modern cipher technology and then say I didn't send it. Unless somebody, once again, had hacked my machine and had access to my keys and was basically spoofing me. But I can't necessarily, assuming there's nothing like that. The keys have been issued to me by the company. I send the email and I send it to a certain person, and I use their public key and my private key, and they turn around and reverse that using their private key and my public key to decrypt it. Then they're the only one who should technically be able to read that mail, so we maintain confidentiality. But there's a degree of integrity checking going on, or non-repudiation going on, in that I can't claim that I didn't send it because of the mathematics of how these modern public-private key encryption works. And so there are a lot of value. We can encrypt communications, so we can encrypt, and we're going to talk about this later in the class, but we can protect the data while it's being transmitted. We can encrypt, like a lot of machines and phones and computers nowadays have disk level encryption, so that unless you have the appropriate authorization, key, face print, biometrics, whatever it is that you log into your machine with, your device with, then it encrypts and you have the ability to use it just like normal. But if somebody was to steal that phone and try to take that, that computer and take that drive out and try to read all that information would be encrypted. So we're maintaining the confidentiality, But the other thing we can do is, because we can sign things, sort of like those checksums for software, we can maintain the integrity too. We can ensure, and we can do that even as part of, say, an encrypted communication. I can encrypt you in a message with an attachment that in addition I have signed to validate that, and produced a checksum value, so that when you get the message, you can decrypt it and then double check that it was the file that I sent and make sure it was the same file I sent. Nothing has changed in transit. And so, as I said, the two biggest pieces of the promises, the two of three that encryption really helps us with, is the confidentiality piece, our promise, and the integrity piece. Indirectly for the availability, especially if by protecting your backups in some kind of major event or breach or something, you were down, all your data was messed up, but your backups were secure and encrypted, and maybe that then allowed you to not have those messed up. And then when you need to restore and bring availability back, you have these solid backups. So there could be a piece of where encryption even helps on the availability piece, but more directly with confidentiality and availability and integrity. And then, as I said, the non-repudiation piece is a big part of that, where, especially using the modern public-private key models of encryption, where I can't necessarily deny that it was me who sent the mail. If my keys haven't been compromised, then it had to come from me. And it also, as we saw with the Network Foundations class and the Open SSH access, that we can use it to authenticate as well and authorize somebody to log in. As a matter of fact, and I know I mentioned that back in the Network Foundations class, but that's the way the major cloud providers, particularly say Amazon Web Services, when you go to create a VM in the cloud, you spin up an instance. You're going to spin up a new server of some kind, web, mail, database, whatever you're doing. When you need to get access to it, what happens is, passwords aren't considered as secure, and so Amazon doesn't even play that game. You could later configure a true VM to take passwords, but by default, when Amazon spins up and creates you that VM and creates you that initial account so that you can get in and be the admin and take over and do things, run sudo, whatever you need to do depending on the version of the OS, you're going to have Amazon, as part of that process, generate a public and private key pair. And Amazon's going to inject the public key into the VM, just like you did in Network Foundations. And you're going to download the private key, store it somewhere safe, set it up with your client. If that's PuTTY, go through the menus and associate that key with that login. If it's, Windows or, a Mac or a Linux command line at the terminal, then you're just going to make sure that you use the right path to the right key when you connect to the right machine, or have them in different folders and switch into those folders and not have to provide the path, but just be able to make sure you're using the right key that goes with the right instance you're trying to log into. So when we look at encryption, when we look at that process of taking plain text and turning it into ciphertext, we really, in the broadest sense, have two ways to go about doing that. We have what we can call a symmetric key. And it means that the key is the same for both sides of the equation. So the best way to think about a symmetric key is pretty much all of the older ways of doing encryption fall into this model, especially the early, more historical ones. And it can even be as silly as something like this may date me, and maybe some of you youngins don't get this one, but the old Cracker Jack box, many times you could get a toy and prize in there, and sometimes it might be a secret decoder ring. And basically, if you had that ring, it had so many letters or numbers or whatever, and if you changed it, then it would show you, what letter or number you were supposed to use in place. So if you wanted to do an A, you wouldn't put an A, and you'd put in whatever that ring was telling you to put in. And then, of course, if somebody else had the matching ring, then they could decipher it by reversing it. These are symmetric keys. We're using the same key. And actually, one of the most famous examples, and one of the first, at least sort of historically known, there probably were other variants that didn't make kind of the history going back that far, but something we call the Caesar cipher. And the Caesar cipher was one of the most, successful early on ways that, basically Caesar was able to maintain communications out through the far Roman Empire without having to worry that every one of the messengers carrying these handwritten letters would be able to just open it up and read everything in it. Despite, wax seals and all that, they, people could peel them off and put another one back on and have read everything. And so Caesar came up with this idea of being able to encrypt his messages to his generals out in the field by using basically what we call an offset. And so even though, of course, there's would have been the Latin alphabet, the principle is the same. We can come up with a code, a key. And let's say you and I want to communicate with each other. And what we want to do is we want to be able to send encrypted messages to each other that no one else can read, at least ideally. And so we decide, okay, here's what we're going to do. We're going to use an offset of 5. So in other words, if we want to use the letter A, instead of putting an A, when it's time to write the letter A, we're going to count over A, B, C, D, E, and we're going to use the E instead. And then, of course, a B would be an F, and all the way to where the letters loop back. And so we're just using a 5 offset. So instead of whatever letter it is, A, we count over. In this case, we're counting that current letter. So 1, 2, 3, 4, 5 would take us out to E. Now, we could have different types of offsets, right? And as we'll see in the next lesson, that's sort of how early cryptography began, is variants on this theme of an offset kind of a key. And there are all kinds of variants, and we'll talk about them next. But one of the big problems, of course, is that you have one key. If somebody gets the key and figures it out, then they too can read those messages. And of course, the other problem is that, Caesar and his generals, for example, or you and I would have to agree. It's sort of like the old spy movies where we would have to drop a briefcase off and pass secret messages, and we would have to agree on what the code was going to be before we can start sending communications with each other. The other major form, and the main form that we see in this day, in the modern age, and that drives a lot, even though symmetric's still there, as we'll learn, is what we call the public-private key model. And this is everything from OpenSSH when we try to log in to a better example actually is probably like most of us do and may not even fully understand how this works. But let's say you open up our browser and you go to the website of your bank. As part of that process, you're going to probably see a little lock symbol or a, welcome Kyle, you're going to see a lock symbol or a little green padlock that shows you that you've got this secure encrypted connection going on between the, and actually, Kyle, yours is coming up in about 40 minutes, right? Because I think this is the crypto class I'm starting this time, and then you got web app security, but you're more than welcome to sit through this one if you want to. But so with that in case, what happens is your browser has actually generated a public-private key pair, and it provides the public key to that website. And the website itself is providing you back a certificate that has its public key, but it's also been signed by a third party. It's another variant of the same thing. And so at that point, behind the scenes in your browser, unless you see an error, you won't even see it. It'll just go green. It actually goes off to that third party and says, hey, I've been presented this certificate by somebody who claims to be, ABC Bank or whatever it is. And so can you validate that for me? And the issuing party, which is usually somebody like Network Solutions, GoDaddy, Cloudflare, one of the registrars, one of the SSL providers out there, they will have done their own encrypting of that. They will have signed it with their own public key. And then they will be able to validate, yes, that is the key. That is, that machine. If you're getting this key from them, we've validated that's the bank. It's on this server, that kind of stuff. And now your browser can trust that public key. And now that you've exchanged public keys, it becomes an easy public-private key model. When you want to talk to the bank, you use your private key and the bank's public key, which you've now validated from the third party, to encrypt traffic that way. And when the bank wants to talk to you, it actually uses its private key and your public key and encrypts the communication back. And you establish a communication connection. And one of the things that's funny is that actually, like I said, symmetric keys are still around. When you finish that initial handshake, once your browser has validated and you guys have had the communication between the browser and the server, and we've set up this secure connection, actually the first thing that happens is that a symmetric key is shared, and that is what you use to encrypt the rest of that communication while you're talking to your bank or Amazon or whoever it is. the reason for that is that the overhead of doing all the math of public-private key encryption can be pretty onerous. And so if everything had to be done that way, then we would it would be much more burden on the servers as well as the browsers and the clients and our computers to calculate all this. Whereas symmetric keys are actually fairly easy to calculate. The problem is that how do we exchange it? Do I have to go, when I create a bank account, they give me some key that I can use to communicate? No, what happens is we use the public-private key to set up that initial, because anybody who has a public key can use it to communicate. So as long as I have the bank's public key, I can encrypt the information with my private key. And the way that works mathematically, only they who have the matching private key, and of course they have a copy of my public, because everybody has everybody's public if you want them. They're all out there, or can be exchanged freely, but it's the private that's the secret part. But because of this cross, where we're using our private and their public, and then they use their private and our public, that's the key that unlocks it. And only they should have their private key, only I should have my private key. Then we have this secure mechanism, and this mechanism, without having to have met in the first place, we can start up one of these communications. Once that's established and we have that encrypted pathway, then usually the bank or the company will provide us a symmetric key. And from that point on, our client and browser will talk and encrypt using that key. And it's only used for that session. And as soon as we break down, log out, that's all shut down. Next time we try to log into the bank and I will go through that same handshake. We'll do the public-private key encryption, set up that communication pathway, and exchange a different symmetric key. So in the real world, we're actually using a hybrid model of public-private key encryption with symmetric encryption underneath. So we're using the public-private key part to be able to exchange those keys at a distance, so we don't have to have met in person before, or use some other means to be able to share that information. But we use the symmetric keys on a regular basis because they're more efficient to operate. So Caesar's first Caesar cipher was just an offset, and you can either way, you can go left or right on the alphabet, and you can do this with any language anywhere. And as you see, as we move into lesson 2, there's a whole bunch, and I'm not going to go through them all, but there are so many variants of these different offset type of ciphers that existed. And some of them, instead of going a standard, they're not just going every 5 or every 3 or whatever, those are variants on a theme. Sometimes maybe they zigzag through the thing. We can even do other things if we really get creative. People have used books as keys before. And so you send a series of numbers, and when you do that, that's referring to, like, maybe it's a 2-number system. So you have number, comma, number, comma, number, and basically that's telling you the page from the book and the word from that page, and that's a way to build up. But we still have, just like with the offset, we have to decide what's the book, what's the pattern, what's the key. We have to have pre-shared that, and that's a weakness in those type of keys. But there is even a more damning weakness, and it's what's led to us, generally speaking, not relying primarily on symmetric keys anymore as the first point of communication. And that is because if you can capture enough of the communication that's using an offset key, you can ultimately break it. And I mean you, as people, students in this class, people taking it. I was a kid, and I can't remember if it was like Hardy Boy novels or Cracker Jack rings or whatever things. I got into this kind of stuff as a younger kid. And basically what you have to do, and you will even do a little bit of this in your lesson, is you will set up, you will say you've captured that message. So you can see it's all strange letters. It doesn't make any words. Nothing makes any sense. So it's all scrambled. It's ciphertext. What can we do to break that? Well, we can use a concept from statistics, which is actually a fairly easy statistical concept called frequency distribution. And the idea is that we can look at the whole pool, all the letters in that communication, and we can basically count up all the different times that those letters show up. When you do that on a ciphertext, then what you do is you kind of do some mapping and a little bit of common sense and play a little bit like crossword puzzle, and you can ultimately work your way into breaking. Well, how does that work? Well, it's because in every language, and it varies to some degree by the language, of course, but in English, for example, the most common letter is the letter E. almost every time any significant block of text, you know, paragraph, 2 paragraphs, multiple pages, a book's worth, if you run the analysis or you feed all that into a computer program, have it count up all the A's, B's, C's, D's, D's, F, G's, etc., and when it comes back and gives you that frequency distribution, the most common letter will be the letter E. And there are actually 5 very common letters in the English language: E, T, A, B. Oh, hold it. No, sorry. I'm reading my note. Yeah. No, it's a D. D and I. Sorry. So E, T, A, D, and I. So we have some vowels, not surprising. The E and the A and the I, very common vowels in our languages and most of our words. And then T and D being 2 of the very common consonants. And you can, that'll go on down, the 6th most common letter, the 7th most common letter, etc. Now, in any subset that you're looking at, that may not absolutely map, though more times than not, you'll find E is the most common letter. So if you take a sample of cybertext and you basically do the math and you come up with the letter Q is the most common letter in that that block of cybertext, then you can assume that that Q is probably an E. Now, if it's a simple offset, then that's going to be that may break it right there, because how many letters is between E and Q? I'd have to count all those. I'm not going to, but whatever number of offset is, if that was the pattern, and once we knew the E, then we could just offset every other letter and possibly decipher it. But let's say they were getting a little more creative than that in some way, shape, or form, you know, different levels. It's still, we could work our way through this, because we would just say, okay, fine, I'm not sure if that's the offset, but I'm pretty sure that these Q's are all going to be E's. And of course, one of the ways you could look at it, especially if there's any spacing that's already indicated in the letter, is you might be able to then see a lot of those Q's, which we think are E's, as the end of little words, like blank, blank, E, THE, for example, right? And etc. And so the idea is that you go through the frequency distributions, you assume and try, fill it in the blank, so to speak, the different things. And so since T is one of the more common letters, if you see one of the top 2 or 3 letters in your list of frequency distribution seems to always begin little 3-letter words, and then that Q, for example, or the most common letter always is the end of those, then we probably have the word "the" multiple times and if we see that pattern, then we can assume that that's the case. And now we know what H is, and you start replacing these, and it's almost like a crossword puzzle, except without the crossing. You're just trying to figure out the words, more like a word match, I guess, or a guessing game. So once you have so many letters in each word, and you start to realize the patterns, of course, to that, okay, well, this symbol or this, and it doesn't matter, like it could be totally different. Like it doesn't even have to be letters. I could send you a message that I turn every letter into a little symbol. There's one in the system called Pigpen, which is a variant of that theme. And so every letter in my message is actually replaced by a symbol. If you know the pattern, the key, then it's easy to break. But if you don't, once again, you can do this frequency distribution analysis and generally start to figure out what in the heck's going on with these letters, right? And so you're going to be exposed to a whole bunch of different, there's what's called the rail fence or zigzag cipher, the Pigpen cipher, which is a symbol substitution, still an offset cipher. There's the one called Vigenère, I think is how it's the best pronunciation I've found. Vigenere, Vigenère, I believe is the appropriate French pronunciation. It says changing the base. It's basically sort of a multi-layer one. We're changing the offset each time. And so we have all these different things. We even talk about one of the still most secure, especially from a symmetric point of view, key out there is what we call a one-time pad. And this would be a case, you might see this in some kind of secure facility, nuclear launch silos, theoretically, or something, you know, some kind of base, some kind of very, very secure facility where basically copies of this pad have been made. A couple, so I'll make one and I keep it for me and I give you one. And every time we encrypt a message, we're using the key that's on that pad. And we use that key to encrypt our message. I tear it off, I send the message to you. You use the key, the reverse, you reverse it with the key, you write the message out, you tear that off. And then next time when I send a message or you send me one, we're always using the top and we're on the same key. We've exchanged those in advance. And because we're not repeating patterns, even if somebody reads multiple messages over a matter of days, weeks, months, whatever, they're not gaining an insight into, as a matter of fact, frequency distribution may foil them because one week the most common letter might be Q, and the next week it might be something else or whatever. So it's changing, and so it's like patterns within pattern and becoming very hard. But the problem, of course, is it's still a single set of symmetric keys, and if somebody gets a copy of that pad, right, spy camera, and shoots them all, then they can follow it and break every message. And we had to pre-share those keys. We had to share that pad. And then, of course, you get into some other things like, and there's a lot of discussion about this in the lesson about the Enigma machine. The Enigma machine was the German encryption machine that was used, for a long time to stymie Allied efforts to crack that code and to provide a confidential means of sending military instructions and orders between the different far-flung German empire during World War II, effectively across Europe. But over time, thanks to various people, including Alan Turing, that code was ultimately cracked. And then the ability of the Allies to know what was going on, really started to impact and even change the war outcome over time. And so one of the things that is also mentioned just sort of as an extra piece in lesson 2 is something called pseudo-random numbers. It's kind of one of the biggest drawbacks to computing and encrypting is that in reality, computers aren't random. They may seem like it at times, and admittedly, some external force like a shock or a cosmic ray or any kind of conflict between two different pieces of software, all kinds of things can cause them to have problems. But they're generally not just random. They don't just randomly decide to do things. There's a reason 99.9% of the time as to why something happened, even if it's something like just the strangest quirk of the fact that maybe one of the values in RAM got hit by that rare positron or particle or something that blew through, and it just threw off the math and it causes a crash, and we can't replicate it ever. Never will happen again. Otherwise, other things are more common. They happen all the time. Every time you boot up your computer and you fire up X, things crash or you get errors. Well, there's some conflict between some of the software. But computers do what we tell them to do. They're very mechanicalistic, zeros and ones at the end of the day. And so they're not random. And that's actually part of the problem with technology, because whether it be encryption or in gaming or whatever, the reality is, since computers aren't random devices, they're deterministic devices, the best they can do is create pseudo-random numbers. And so they will usually, use some kind of very complex algorithm to generate a string of numbers that, for all practical purposes, seem random. But the reality is, if you can get your hands on that algorithm, or in some cases you give that algorithm the same seed value, then it will calculate the exact same set of answers again. And since we depend on a lot of randomness to ostensibly help us, make it so that people can't use frequency distribution and other types of techniques to break our code, this is one of the weaknesses, and where some people feel that a number of different things in future, including maybe quantum and others, will help in that capacity. I actually saw an interesting kind of one of the crime shows, CSI, FBI, whatever it was. I can't remember now, it doesn't matter. But just the other night, my wife and I were watching it, and kind of one of the central parts of it was a company was supposedly using the randomness in lava lamps as a way to sort of their secret sauce of how they added an element of randomness to their encryption services that they were offering to enterprise and state players, and so it was an interesting concept whether that would really work. But I mean, when we generate, sometimes a lot of times, especially if there is a GUI environment to do it in, like if you were to use Putty's Gen to generate a key, it tells you to move the mouse around a bunch because it's kind of reading those numbers instead of just calculating some formula that it might calculate the same way for somebody else. It ostensibly is using your random mouse movements to help generate the random numbers to it. So there are other means like that come into play. So one of the things I always point out is that, especially in lesson 2, you are going to spend a fair amount of time getting to play with some of these ciphers. There there are some websites out there that you can go in and put in values, and it will generate the cipher, or vice versa. And so you're given different assignments to work with some of those, and to encode certain things, and to decrypt certain things, and even do some of this frequency analysis. It's a lot of fun if you ever have any reason to. Now, admittedly, like I said, the first time I did it was probably for Hardy Boys or whatever, and then I remember actually the only time I kind of semi-practically, and I did variants of this twice in my life, but when I was very young, like grade school level, there were a couple of young ladies in the class that were constantly passing each other notes. And where exactly they learned this, on their own, or maybe their dad taught them or something, I don't know, but they were using a cipher. And the reason they were using the cipher is because the teacher in that class, if she caught note passing, would shame whoever passed the note. She would stand up in the front of the class and read the note. And so these young ladies had seen that happen to people be embarrassed because they admitted crushes on somebody, or whatever the case is, or just communicating and being silly. Or at least once, I remember, it was one of the funniest things I ever saw in grade school, was somebody was passing a note and they were bad mouthing the teacher, and the teacher confiscated that note and then read it, and of course was even more mad than they were passing a note, because they were talking bad about them. But nonetheless, so these young ladies were writing these notes to each other and slipping them, and I was watching them, like, a row over and up. They would slip it whenever she wasn't looking, and then weirdly enough to them, they weren't keeping them. They would just sort of like stick them in the underneath the desk, like these little slips of paper with this gobbledygook on it. And they would pass them back and forth, write their notes, and then they would just leave them there. They were so convinced, I guess, that no one could ever read them but them, because they knew the code. And let's just say that after gathering some of those and using some of these techniques, I was able to break that code. And for the rest of that year, while I was in their class, I knew, who liked who kissed who at the party on the weekend. It's a skating rink, or just silly, grade school, fifth, whatever, sixth grade kind of stuff. But nonetheless, it was a practical application of being able to break a code. And so you're going to play with some of that in this lesson 2. Now, lesson 3, we introduce a concept that is actually pretty critical to cybersecurity, and definitely fits into this whole cryptography and even access management discussion. That's why it's here. And that's what we call the states of data. When it's actually one of the things that I sometimes say when I define cybersecurity, is I'll say, our job is to protect the organizational information in all of its states. And I may have even said that way back to your first security foundations or whatever classes, but never really defined the states. What do we mean by that? Well, there are 3 states of data that data can be in. Data can be in use. And so if we're actively writing on code or a document or doing something, running it on the computer, that's in RAM, right? We all know how that works. Everything lives in RAM. So if you're writing a new document and you shut off the power goes off and you haven't saved it, then that was in RAM and it goes away. But that's in use, so that data is in use. And then, of course, if we save the data and we save it out to a file like our resume or our report.com or report.doc, whatever, then that data is at rest. It's sitting on the storage system. It can be a hard drive, magnetic tape, platters, it doesn't matter. It's at rest. And then, of course, the other state of data that's pretty common, and especially in our client-server interconnected world of the webs, is we have data in transit. So we have to protect data in all of those states when we're protecting the data of our organization. And so this involves needing to be able to protect data when we transmit it, potentially within our organization, definitely external to our organization. If we're communicating sensitive information, say trying to process a credit card payment or share information about our customers with one of our partners, we don't want to just send that out in plain text especially if there's a lot of personally identifiable information in there. So we would want to use some form of encryption, right, to be able to encrypt that information and send it off. When we store data, we also have the same need. It boggles my mind that in this day and age, it still happens that one of these breaches, when you read about its report, somebody will have broken into XYZ company and stolen all the user files, and still it's admittedly a minority now than it was, say, 5, 10, 20 years ago, definitely in the early days. But it still boggles my mind that you'll find and you'll read about a case where a breach has happened, tens of millions, hundreds of millions, whatever records are stolen from this company, and all of the passwords and information inside of that file are just plain text. So once you have it, you know exactly what to do. You have their email, you have their password, you have everything. More and more, what we'll see is that if not all of that data, at least the critical data, social security numbers, credit card numbers, passwords, etc., are going to be encrypted in the database. And so while that data is at rest, if somebody steals that file, they still don't necessarily have, all the personal information like social security cards and numbers and things like that. The biggest challenge, so encryption, as you can see, can definitely help us, and it makes total sense. We encrypt all the communications between ourselves and our bank, between ourselves and Amazon, all of, more and more, if not, it's sort of Google's goal to turn everything into HTTPS. They are actually, they sort of take down search results for people who don't have that, which I kind of get to a degree, but also it's a different little soapbox and a different issue, but I find it kind of annoying that everybody thinks everything needs to be encrypted. Why do we have to do the overhead of encrypting between the client and the browser, whether that's a phone or a desktop or a tablet or whatever, when all somebody's doing, if say I'm a restaurant and they're looking at my menu. Now, some people would counter, well, if somebody's tracking you and now they see that you've gone to that restaurant page and so you're looking at the menu, you're probably going to go eat there. Well, yes, but if they're tracking me, if they have something on my machine, it's not going to matter. If they're just tracking me through cookies or whatever, they'll still know I went to that site, whether I encrypted everything I talked. So they may not know that I booked a reservation or read the page, or I just, went and, they may not know what I did. But once again, if they know I visited a restaurant site and spent a fair amount of time clicking around a couple of pages there, they're probably going to assume I'm going there soon, and maybe they'd set up their stakeout for me there. So, I mean, I just don't get the value of encrypting certain stuff that is just purely open and meant to be public information. At least from that provider's point of view, maybe somebody would have a reason they would like to have that encrypted. But that is the world we're moving to, where everybody, particularly Google and some of the other major players, are pushing everybody to encrypt everything. So we can do that when we transmit data, fairly easy. Even if we're using this hybrid model of the initial public-private key handshake to then exchange a symmetric key. And we can obviously encrypt data, and sometimes in more than one format. I've seen people who are, kind of really concerned about it, or maybe there's a need in their organization, but they might have a particular file or database or something encrypted itself, and that's on an encrypted hard drive that's being backed up to encrypted tape. Okay, so encryption can help when we have data at rest, and it can help when we have data in transit. The problem is, and where we run into the weakest and where encryption does next to nothing, if anything at all, is when data is in use. If you think about this, if you're an employee at a bank and you pull up somebody's record, yes, we could have stored that information in the database about that person, their social security number, all that stuff encrypted. Yes, when it was transferred from the server to our workstation, it probably came in encrypted, so nobody could get it on the wire. But if it showed up as cybertext and ciphertext and nothing that I could read or work with on the screen, then I wouldn't be able to do my job. I wouldn't know if I had the right record. I wouldn't know how to add another transaction or modify one if I couldn't read it. So when data's in use is the problem. When data's on the screen, generally there's a human there reading that data, an account person, a customer service person, whatever it is, and they have to be able to read it. Your accounting people have to be able to read it to create another entry or to make sure they're applying the payment to the right bill. It can't be ciphertext in that format. And so this is where encryption doesn't help us, is when data is in use on a particular device or machine. And so somebody can see it. And so this is where you'll see other things. I know of a couple instances where very high secure call centers, where the customer service people obviously have to be able to pull up records on the screen to be able to process that service call, whatever it might be. Well, if it's very, if there's a very secure environment there with a lot of personal information, say like addresses and social security cards and credit cards and all that, well, that may come up on the screen for that rep to be able to help support that person, answer that question, do whatever they need to do. But to protect it, there may be all kinds of other both policy and technical and physical controls that are put into place to protect that data. So for example, if it's really critical that data not get out, that those customer records not leave that organization, you will find very likely a station that they're working on that has no ability to take a print screen. It has no ability to print to anything. It has no ability to let you put a USB stick in it, so you can't take that data off. It has no connection to the outside world. It's air gapped. Maybe it's internal. You have internal email, and through the appropriate proxy, which is being filtered and looked at, you can send to customers. But you can't just say, take a bunch of data screenshots you've been making and send them to your own personal email account. And I've seen those kind of environments. And if the data is that important, that's the extra steps you have to go to: physical security and policy procedures and controls in place that'll protect the data while it's in use, because those reps have to be able to pull up and read that data and use it. So in addition, there is a numerous talk. We talked about how, when in motion, we have various protocols. We talked about secure protocols before. So if you were wanting to have, remote control of a server, you want to use OpenSSH so you can encrypt that communication channel, and the passwords and things don't just go out over the internet in plain text. If you were using Telnet or FTP, then that would be the case where it's not secure. And so obviously we want to use the secure protocols and the most advanced and updated versions we can get. When we're talking about encrypting things on, for data at rest, we can encrypt whole file systems, we can encrypt whole databases, we can corrupt individual files, individual parts of records. Could be that, maybe some of the information, because it's a big customer database, some of the information, name and stuff, is not encrypted, but other information like social security number, credit card number, date of birth, other things is encrypted, usernames and passwords, obviously, so that if somebody steals that data, they have to do an additional step to try to break into it. And so, but once again, like with all security controls and measures, it's a matter of we have to decide, where to draw those lines. Now, there are a couple other concepts thrown in. With regard to the start to dev into, or we're going to talk about access controls more next week, but you're going to find MFA, which is multi-factor authentication, and access controls come into the discussion. We'll talk more about them in the coming days, but that's obviously one of the things. If you remember going back to early class as well, so your first class, when we talked about PCI DSS, one of the rules that they put in place is that everybody who has access to that credit card information must have a unique logon to the network. And that is an auditing mechanism. That is sort of acceptance of the fact that, okay, we can't encrypt that data while it's in use, so we have to track who's using that data. Because if this company has a breach and somebody internal, for example, steals a bunch of credit card information and shares it with a nefarious friend, or sells it on the dark web or something, and and the PCI traces that back to us, and they come in and do an audit. If all of our accounting people use the same username and password, then we can't account for who was the one that was into those records, who was the one that could have stolen those records. Whereas if we have a unique username and password for each person that logs in, and we're enforcing that and tracking that, then if a certain 1,000 records get stolen, and we go back and look at the history and see that Bill was the one who was processing payments on those very accounts, we figure out that, I don't know, what did they do? Take a photo of everything, since they shouldn't, or did they take screenshots? Did they just write it down in a notepad and send us, here's these credit cards, and send them to themselves? What did they do? But we can figure that out, but at least we know who to look at. Whereas if we're sharing that account information, we don't. And so this is where the reason these two come together is because, of course, a lot of our authentication, like say logging into an AWS instance or to your OpenSSH server on a VM somewhere, you're using encryption as part of that login process. But in addition, because not everything can be encrypted, particularly while it's in use, we want to use access controls to monitor and log who's in the systems and who's doing what, so we can make sure that we're maintaining our security and that we have an audit trail to go see what went wrong if something goes wrong. And so there is a little bit more in there, including some best practices and a little bit about risk assessment. At the end of the day, like so much in cybersecurity, we have to do our own risk assessment, decide where our risk, where we fall in this. Like I've said before, two companies with websites, one makes $1 million an hour and one makes $5 an hour. This person is going to spend a lot of money to protect their website and do more, and these folks probably aren't. Same kind of deal. If somebody's like Amazon and has billions of bets of data on various customers all over the world, they're going to do a lot to try to protect that. Whereas somebody who doesn't have any information stored in a database that would be considered, personally identifiable information. They don't store credit cards. They don't store social security numbers. They don't have a loyalty program. They don't have anything. Maybe some people signed up for a newsletter. So at worst, I'm not saying that emails aren't a bad thing to lose, but there would be a lot less impetus to protect that data on that little small website than there would be on Amazon's website. And so at the end of the day, that where we draw our lines, how much encryption, how many layers, how that fits into our overall cybersecurity policy is always driven by the risk assessments that we do. All right. So that wraps up lesson 3. Next week, and I'll post that schedule later, I think I'll be back to the Tuesday, Wednesday, middle of the week model. This is a one-off that I have to bebop into the evening and the Wednesday morning before I go out of town Tuesday night briefly for a Tuesday morning or Wednesday morning meeting, and then I'll be back. So it just, like I said, complicated I went ahead and did the workshops today. Well, that's all I have for you. Here in another few minutes or so, I'll kick back up and be doing the web application security part for the web application security and project management class. But that's your first 3 lessons for crypto and access management. And we'll talk to you soon. Thanks.